This is Professor Hui explaining how you can use wind to generate power. What we have here is that if I have an area of A through which wind blows at a velocity of v, then the mass of air that flows through this area A in 1 second is given by the area times the velocity of the wind. And the mass would be equal to the volume of that flows through times the density of wind, which is roughly 1 kilogram per meter cubed. So the power that's generated is given by 1/2 of the mass of the air flowing through that area per second multiplied by the velocity square. And if you substitute this in, you have a total power output for the area A given by 1/2 of rho times A times the cube power of the velocity. If you have a velocity that's 1 meter per second, you will find out that the power output per meter square would be equal to 1/2 watt. Now, 1 meter per second velocity of wind is equivalent to 24 miles per hour. So if you think about this, if wind is blowing at 24 miles per hour, and you compare the power output to that, which is at 50 miles per hour, what you find is that a 50 miles per hour wind would have a power that is 9 times more than that at 24 miles an hour. Now we're going to do an experiment to demonstrate how you can use electricity to generate wind. What you have here is that we are measuring the wind velocity at the output of the fan, and you will find that the velocity now is given by 4.7 meter per second. It's getting to be close to 5 meter per second. And if you look at the back side of the fan, where air is being sucked in, what sort of velocity are you getting?
We have 3 meters per second.
So we have 3 meters per second compared to about 5 meters per second in the front of the fan. So I can explain then the amount of electricity that the fan is using to push the air out. What we have here is that if you have a turbine, which is quite the reverse of the fan, for which you have high velocity wind blowing in the front of the turbine at the velocity of V in, and at the back side of the turbine you have the output velocity of the wind decreased to V out here. So the turbine would be converting kinetic energy of wind into through the use of an electric motor into electricity. So the power output of the turbine combined with a motor is given by 1/2 of A, the area of the turbine, and then rho, the density of air, multiplied by the input velocity of wind minus to the cube power minus the output velocity of wind also to the cube power. So you really don't need a large number of fans for the turbine. The reason is very simple. If your output velocity is 1/2 that of the input velocity, then the amount of power on the input side is 8 times more than the amount of power on the output side because of the velocity cube power. So therefore, almost 7/8 of the power of the wind is now converted into electricity. Of course, we don't get that much because of turbulence and things of that sort. So typically, the power output of a turbine is somewhere below 20% of the total power on the input side. Next, we're going to look at how we can concentrate wind through the use of an incline. And what you have here is that we have the same fan that blows air up an incline. And so let's measure the wind velocity when the incline is at a very shallow angle.
We have 2.7.
2.7 meter per second. And as you raise it to almost a 30 to 40 degree angle, and we're going to let it to settle down to a terminal velocity.
Now we're at 3.4.
3.4. So it was 2.7, and let me just write this down, which is 2. As the incline this is 2.7 meter per second, whereas at a almost a 30-degree angle or 40-degree angle, it is at 3.4 meter per second. So what you see here is that there's a substantial increase in wind velocity from 2.7 to 3.4. And because the power of wind goes up as a cube of velocity, what you see here is almost like 3/4, which is 64 divided by 9. You almost had a actually cube power, right? So 64 divided by 27, you almost have a doubling or tripling of the output power because of the increase in wind velocity.